So the title of our presentation is Prompting or Fine-Tuning. So we exploring the large language model for causal graph verification or validation. So again, in the introduction, is the conventional way to perform causal discovery is with statistical-based causal discovery, which estimate causal structures from observational data and generate a causal graph as a result. But again, this causal graph from this method is mostly unsupervised, means there is no ground truth, and normally human experts, subject matter experts, are expected to verify the result. For example, in this certain example is during the verification, we might ask whether smoking really does cause lung cancer or whether smoking really does cause yellow fingers. And again, human experts are supposed to evaluate to verify this causality, or other way is to do the controlled experiment where we, for example, assign person to smoke and then we monitor whether this person develops lung cancer, which is, of course, it is unethical, so it's not possible. So this method is, of course, have some limitation. The first is it difficult if we, as our presenter said, it is difficult and also expensive to consult to experts, and also not scalable, especially when we want to evaluate a huge, large graph and we cannot possibly check one by one. And also, sometimes it's also not feasible to do the control experiment because what I just said of like ethical concern, or like when an experiment is involving human subjects. However, this information about causality actually a lot dispersed in many text sources. For example, in the research paper of the other that conducted the experiment, and they have their expert to verify the result. And these sources from the text can actually be used for verifying the causal graph from the statistical causal discovery method. So for example, here I have an excerpt from a paper which shows potential causality between osteopontin, it is a gene or protein name, and how it contributes to the progression of the prostate cancer. So we wanted to extract this kind of causal relationship between pair, and so far there is already study on this topic, which is called causal natural language processing, because it uses NLP method to extract this relationship, and this can be used to verify the causal graph by predicting the causal relationship between each pair in the graph. So here the illustration, we have causal graph at the right, and for every pair, we use the causal NLP either from text sources like the journal or research paper, or like from knowledge base, for example, knowledge graph that is already in the form of knowledge base that also has those variables and the ground truth. So some related works on this causal relation extraction, or some say classification, can be broadly divided into two. The first is conventionally earlier method is using in a supervised setting, which is you fine-tune a large language model. For example, BERT, it's a little bit more conventional because now we have this decoder only model that and now we have this LLM-based prompting method. So but however, it can be broadly divided into these two. It's either fine-tuning or prompting. Based on in the related works, LLM-based prompting usually performs better, especially if you use very new model. But yeah, let's see. So the research question in this presentation is, so we have those two methods, right? This prompting or fine-tuning. So we want to explore which method is actually better, at least for the specific task of causal relation extraction or classification. So again, this is our task formulation. We've given a pair of entities, or which is a variable on the node in the causal graph, for example, smoking and lung cancer. The LLM is tasked with with extracting the causal relationship between each of this pair. And the task is again formulated as a classification task. And here, this time we will classify each pair into whether it has causal relationship or non-causal. So it is a binary classification task, which is related to our benchmark data that only has this ground truth. So the first approach is prompting. So I guess everyone should already know, but anyway, this is a little bit of definition of the prompting itself, which formally the LLM is adapted to specific task. In our case, it is a causal relation extraction task via using a natural language prompt, which is a pieces of text combined with the input and then fed to the LLM to produce an output for that specific task. And in the prompting, it can be broadly divided. We have two types here. First is the zero-shot prompt and also few-shot prompt. I will explain one by one for each prompting method. So the first is zero-shot prompting. Here, the large language model is instructed to determine the causal relationship between a pair of entities directly without being provided with any training examples here. So we just ask basically. So formally here, we will have the prompt, the entity pair, the context sentences, and then we immediately ask the LLM to produce an output, which we constrain here to be causal or non-causal. This will be the example of the prompts. For example, here, is there any causal relationship between A and B in the context S? And here our sentences is the example of the context sentences. And here is the real prompt variation that we use in the experiment. We experimented with several variations. The first is we provide choices to the LLM and without using any context. So here, there is a causal relationship between A and B. There's this statement, and then we ask LLM so whether the statement is true or false, without providing any other context or information. And then the second is we again give two choices, but this time with the context. So we provided the context sentences where the pair appears in those texts. And the last is we give three choices and also including context. Here we basically give more strict condition to the LLM that if you are not really sure, then please answer with maybe instead of binary. And then the second prompting approach is what it calls few-shot prompting, which is different to the previous zero-shot. Here we provided with few examples and specific examples that we embed directly into the prompt, and that it serves as like some kind of implicit supervision so that the LLM can learn by itself what is the task and how to answer without any parameter updates. This is also popularly called in-context learning. So yeah, the different with the previous, here we have the examples and then we give one test and then we expect the LM to answer on this specific test example. I'll give an example here on the prompts. So here our prompt on this few shot, the blue one here is the examples. Here we only include one example on this specific for clarity. And then this red one is the test input. You can see the difference here. We don't have the result on the red one, and we expect the LM to answer with this kind of format following the example that we already gave in the blue part. So yeah, that's the prompting method. We have two, and then the next type is fine-tuning. So LLM pre-training process itself uses a large amount of unlabeled data, so it is unsupervised. While the fine-tuning is basically training the model on the labeled data set and then allow the model to update the parameter for that specific task following our label example. So it requires expert annotated training data in this approach. So here, we have two choices of models that we will use on the experiment. The first is BERT model, which is to represent a smaller language model. It's roughly 250 parameters, so under 1 billion parameters. And then the second is we use GPT fine-tuning to represent larger parameters models. So first is, so we will explain a bit on the BERT fine-tuning. So BERT model, I'm not sure if you are familiar, but it's trained using it's one of the early language model. So maybe not so large anymore because it has quite small parameters. And anyway, for this one, we chose a simple architecture for a fair comparison with the prompt-based method. And then the second is we fine-tune the GPT model as well. And for GPT, it has specific example. So we follow the instruction on the openai.com basically. And then we model this, we fine-tune the GPT using two formats. This is our experiment. We experiment using the BERT model. For the BERT, we use three models, BERT model, BioBERT, and PubMed bird used for the biomedical dataset and the normal bird for the open domain dataset. Again, we use two types of dataset, the biomedical dataset and one open domain dataset. And this is our experiment result. So I will go one by one on our findings. The first is the fine-tuned model apparently outperformed the prompt-based LLM across all datasets that we in our experiment. And even with, so here in general, you can see that on the lower the fine-tuning part, it always has a higher performance. And then even with smaller model, like I said, the BERT is only like a roughly 200 million parameters, it still boosts the performance. So one of the possibilities that the fine-tuning exposes the model to various ways causality can be expressed in text. That is why it leads to better performance. The finding two is the few-shot prompting, which is prompting but giving the LLM the examples, does not always outperform the zero-shot without any examples. We even see one significant drop here, up to 30 points. So the possible of why it happened could be that when the training examples that were provided to the LLM is very small or chosen poorly, it might confuse the model. But yeah, this needs further examination, I would say. And then our third finding is whether including the context sentences into the prompt can be effective. And yes, it is, especially in the biomedical dataset, we observe bigger performance increase. While in the open domain dataset, like newspaper or something, the gain can be small. And so the context and sentence helps the LLM, especially when the internal knowledge is not really enough, for example, for very domain specific, like in the biomedical. Well, in the open domain, most likely the LLM already trained on those like Wikidata or newspaper or online content, which explains why the performance gains is much smaller. And then the last finding is we generally observe higher scores in the open domain compared to the biomedical domain for the exact same reason, because of the pre-training of the large language model itself. Here, this is the biomedical data, and this is the open domain result. And we can see that the open domain, it reached almost 96.8, the highest. Well, for the biomedical, we only observe like roughly 77 F1 scores. So here in this paper, we present a study that explored the feasibility of applying NLP technologies, this causal relation extraction, especially LLMs, for verifying the causal graph, helping human basically. Especially we compare the prompt-based and also the fine-tuning, and in our result in this dataset, the fine-tuning models still perform better than prompt-based, even with a smaller parameters like BERT. However, the fine-tuning model, again, it needs expert annotated data, so could be expensive and difficult. So in this case, LLMs-based method like prompting also hold the promise for a causal inference. So thank you. We don't have a lot of time.
No,
so I will leave it to
one quick question.
You did not use prompting on BERT, right?
I'm sorry?
Prompting was used exclusively on GPT-5
Yes.
models, right? Okay.
Yes, we did not prompt the BERT, of course. It's only on the fine-tuning.
Okay. Just wondering if you had happened to somehow manage to do that.
I don't think so, because BERT is not really generative mode.
I know.
Okay.
But just in case you had done something along those lines or something like
I
that.
did not. I don't think it's suitable for prompting, for using BERT. It's not big enough.
I know, but just in case.
Yeah. Maybe I should try. Let's see. Okay, thank you very much.